Welcome to this explainer, folks. Today, we're diving headfirst into the mechanical alphabet soup of vehicle drivetrains. We're going to uncover exactly how your car manages traction. Whether you're navigating a slick, wet suburban street or trying to crawl up a steep, rocky mountain pass, understanding what's actually happening underneath your vehicle is the key to maintaining control. So today, we are pulling back the curtain on how engine power is translated into forward momentum. Here's our roadmap for today. We'll start with AWD versus 4WD basics, move to the transfer case, break down 4H versus 4L, tackle the drivetrain binding problem, and finish up with differentials and ultimate traction. Let's get into it. All right, Section 1, AWD versus 4WD basics. So to kick things off, we really need to clear up the biggest point of confusion out there. All-wheel drive versus four-wheel drive. Here is the baseline difference. AWD, it's all about computers predicting and reacting to slip on the fly. You just drive, and if a wheel hits a patch of ice, sensors tell the computer to instantly redirect power to the wheels that still have grip. But 4WD, that's a part-time setup. It literally requires you, the driver, to mechanically lock the system, usually by grabbing a lever or turning a dial, for those really extreme, low-traction environments. Now, what's really fascinating here is how AWD pulls off this flexibility. It actually relies on three completely separate differentials, front, rear, and center, to manage torque automatically. And that center diff? That is the absolute magic piece for all-wheel drive. It lets the front and rear axles rotate at slightly different speeds. This is exactly why you can drive an AWD car on perfectly dry pavement without completely destroying your transmission. The system dynamically gives and takes power at all four corners. Moving right along to Section 2, the transfer case heart. So, in a true 4WD setup, you can forget about that center differential. It's gone. Instead, it's replaced by a transfer case. This acts as a rigid, physical lock to guarantee that engine torque is always sent to at least one front and one rear wheel, no matter how much they're slipping. If your back wheels are buried deep in mud and spinning freely, a computer-reliant system might struggle, but this 4WD system doesn't care at all. It physically forces those front wheels to turn at the exact same speed, pulling you right out of the mess. Let's actually trace that path of power step by step so we can see how this rigid mechanical chain gets you moving. It starts at the engine, right? Creating a rotational force, or torque. That power travels to the transmission and then hits the transfer case. When you engage 4WD, gears inside that transfer case lock together, splitting the power a perfect 50-50 to the front and rear drive shafts. From there, those drive shafts carry the power to the front and rear differentials, which finally spin the wheels. It's a completely unbroken physical chain of power. Okay, Section 3, 4H versus 4L explained. Once you're actually using that transfer case, you've got a choice to make depending on the obstacle ahead, 4H or 4L. 4H, or four-wheel drive high, keeps your gear ratio near 1:1. It's perfect for maintaining speed on moderately slippery roads, like light snow or gravel, and you can usually just shift into it on the fly while driving. But 4L, that is an entirely different beast. It strictly requires you to stop the vehicle, shift into neutral, and engage a completely different set of super low gears inside the transfer case just for off-road crawling. And just look at this number, 2.6 to 1. By dropping into this specific low-range gear ratio, the transfer case multiplies the engine's torque output by more than 2.5 times. That gives you this immense brute force pulling power at just a walking pace. Think about trying to crawl up a steep rocky trail or pulling a heavy load out of deep sand. You don't need speed there, you need raw force. In 4L, the engine runs at higher RPMs relative to your wheel speed, delivering massive force per rotation. I absolutely love this quote from the sources because it perfectly grounds all that technical gear ratio data into real-world driving. 4H is a traction boost for driving, 4L is a power boost for crawling. Seriously, if you're going over 25 miles per hour and just need some extra grip, use 4H. But if you're barely moving and need absolute maximum torque for crawling over a boulder, you're definitely in 4L territory. Which brings us to Section 4, the drivetrain binding problem. Now, you might be wondering, if 4WD gives us this ultimate, unstoppable grip, why not just leave it turned on all the time, even just driving around town on a sunny day? It sounds logical, right? More traction is always better. Well, doing that will actually destroy your vehicle from the inside out. Enter the real antagonist of our story, drivetrain binding. This is a highly destructive phenomenon. Picture this, you're taking a right turn. Your inside right wheel is traveling a much shorter distance than your outside left wheel, meaning the outside wheel has to spin faster to keep up. But remember, a part-time 4WD transfer case absolutely forces the front and rear to spin at the exact same speed. On dirt or snow, the tires can just slip a little bit to compensate. But on perfectly dry pavement, they grip completely. Because they can't slip, all that stress travels straight up the axles into the transfer case. The gears start literally jamming and binding together. You'll feel the steering get incredibly stiff, you'll hear loud clunking, and eventually, expensive metal parts are gonna snap.
All right, our final section, Section 5, Differentials and Ultimate Traction.
To solve that wheel speed geometry problem we just talked about, we rely on the final stop in the power flow, differentials. The most common is the open differential. It's cheap, and it beautifully lets your wheels spin at different speeds during a turn on dry pavement. But off-road, it can be your worst enemy. Because of physics, it sends power to the path of least resistance. So if you're on a trail and one wheel lifts up into the air, literally all your engine's power goes straight to that airborne wheel. It just spins pointlessly, while the wheel firmly planted on the ground gets absolutely nothing.
That exact problem is why the Limited Slip Differential, or LSD, is such a massive upgrade. It manages to balance smooth cornering with the ability to push through uneven, slippery terrain. If one wheel hits a mud puddle or lifts into the air, the LSD mechanism actively limits that slipping and ensures optimum torque is still sent to the wheel that actually has grip. So you get the smooth street cornering of an open diff combined with a huge boost in off-road capability.
Now, if we go to the extreme end of the spectrum, like specialized ATV racing, builders might use a spool in the rear. A spool isn't even really a differential. It's basically a solid piece of metal that permanently locks the two rear wheels together. It's incredibly light and has minimal power loss, meaning absolute maximum power hits the dirt. But because it has zero give for wheel speed differences during turns, it induces extreme oversteer, which is, perfect for sliding an ATV around a dirt track, but absolutely terrible for driving to the grocery store.
Seeing a standard layout next to a modified spool setup really highlights how altering just one piece of this mechanical alphabet soup completely changes a vehicle's handling. Swap out a rear diff for a spool, maybe throw a limited slip differential in the front, and engineers can completely tune a vehicle's traction bias. It just proves there is no magic one-size-fits-all solution. The mechanics really have to match the environment.
At the end of the day, understanding exactly how torque flows from your engine to the dirt empowers you to navigate treacherous terrain safely while avoiding costly mechanical mistakes. When you actually know why drivetrain binding happens, you're never going to accidentally leave your truck in 4H on dry pavement. When you know exactly what that transfer case is doing, you'll know precisely when to drop into 4L to conquer that steep, rocky incline.
So as we wrap up, I want you to think about your own vehicle's capabilities. The next time you face a slippery incline, are you going to trust a computer's sensors to figure it out, or are you ready to engage that transfer case and manually lock in your mechanical fate? Understanding these systems is the absolute first step to mastering them when the pavement ends. Thanks so much for joining me on this explainer. Keep learning and drive safe.